and welcome to Maths on the Move, the podcast from plus.maths.org. I'm Rachel Thomas.
And I'm Marianne Freiberger. How are you today, Rachel?
Well, I'm a bit damp, actually. This morning, it was really beautiful and sunny, so I went into the garden for breakfast and a little spot of gardening before work, and then the clouds headed in and it rained on me.
Well, yeah, that's because data on current conditions isn't always reliable. I tend to check the weather app on my phone. Instead of just relying on what we can see right now, this relies on mathematical models that incorporate the laws of physics involved in the processes that affect the weather.
But the weather app isn't always that reliable either. As we know from previous interviews, we'll put some links in the show notes, that the weather is a very complicated system. But excitingly, we're going to hear in this podcast about some very, very new research that might just help. So in this podcast, we're going to hear from Georg Maierhofer, one of our colleagues from the Maths for Deep Learning Research Project, which is known as Maths for DL for short. And Georg's going to tell us about how we might be able to bring together the very new science of artificial intelligence and machine learning together with the laws of physics to make even better predictions about the real world. Here's Georg starting us off by giving an example of what this means, and that involves learning how to play golf.
Maybe one way to think of it is if you want to learn a new sport, right? So let's say you want to learn how to play golf. And if you've never seen any object drop in the influence of gravity, it's really, really difficult to understand how you should move your arms to hit the golf ball and to make it move in the right direction and the right distance. But if you have played some other sports, let's say tennis or something like that, then you know how an object moves and how it falls. So you know inherently about Newton's second law, essentially. That means you have some differential equation, even if you don't think of it, at the back of your mind. And then if you want to learn to play golf, and you know that in the back of your mind, it's first of all easier to learn it in the first place. But secondly, it's also much easier to then adjust that based on new data that you get at the moment. So if there's some wind or something like that, and you know how the golf ball behaves without the wind, it's pretty easy to, or much easier to then incorporate that and adjust your swing accordingly once you've got a basic understanding. And it's this kind of physical knowledge that we give machine learning. Yeah.
So Georg was saying that even if we don't realize it, our experience of the world means that we have an understanding of the laws of physics in the back of our minds. And in mathematics, these laws of physics are often written as differential equations, which Georg mentioned.
And many of us actually have a differential equation like this at the back of our minds, which is Newton's famous second law of motion, force equals mass times acceleration. And these laws of physics give us a mathematical model that we can use to make predictions about how the world works. Here's Georg again.
When you think about making predictions in the real world, what we classically do, what we've done so far, and even these days, I think is the most widely acceptable way of making sensible predictions, let's say about the weather or about the structural integrity of an airplane or something like that, is you start off by making a model of the physics. So you write down, for example, a differential equation that describes how that system should behave. And then you take a computer and you approximate the solution of that differential equation. And so these are really sort of coming from an understanding of the physics in the first place. And so in the recent years, there's been quite a significant push to use machine learning methods to try and make predictions about the real world.
So now we get to where machine learning comes in. Marianne, you recently discussed how machine learning works in a recent podcast with Kwaku Abrahams, who's also from Maths for DL. Do you want to give us a reminder of how machine learning works?
Yeah, so machine learning is the big and relatively recent success story in artificial intelligence. And the idea is that in machine learning, rather than explicitly giving instructions to a computer on how to do a task, which is what happens in a traditional computer program, the idea is to let the computer learn for itself how to do the task from repeatedly doing it. And you're also given it some way of judging how successful it is or how to improve. This is often done using something called a neural network, which is basically a big mathematical equation which takes inputs, say data about the weather for the last week, and then produces outputs, say if it will rain tomorrow. A machine learning algorithm sets the neural network up to run through loads of inputs to produce outputs, which are predictions, for example, about the weather. And there is also a method for how to tweak or tune the neural network. That means tweaking sort of internal parameters of this big mathematical equation to hopefully improve the predictions. And this process of improving the predictions is called training the neural network. Here's Georg again talking about the recent push to use machine learning to make predictions about the real world.
It's a little bit more challenging to understand what information you provide the machine learning algorithm in order to make that prediction in the first place. And physics-informed neural networks, so PINs, they came about maybe 4 years ago, roughly, as a first idea. And the idea is that you provide the machine learning method when you train it, when you tell it what it should know about nature, a bit more information about the physics that we already understand. So if there is a system where we have a differential equation that describes that system, you can incorporate that into the training phase of the neural network. And that allows the neural network to make better predictions.
I didn't realize PINs are so new, only 4-5 years old.
Yeah.
At the moment, like, what have people been able to do with them? What are PINs good at the moment?
Yeah, it's again, I think it's a really interesting time to work on those because they are so young, and because I think there is significant opportunity in the use of those methodologies, but they are not able to compete in a sort of large-scale industrial setting with anything that's been there classically yet. So we see some early advantages of using PINs in a sort of research-based setting, but they're not yet able to sort of scale up and provide the same sort of reliability and very certifiability that you have with the sort of classical methods. But I think one of the really nice things about or the potential in there is that when you train a neural network, you don't have to give it a lot of information about how it should approach a problem. So you provide it with a task, let's say predict the weather for tomorrow, and you tell it, this is the information I can provide you. For example, there's a physical law that we know governs the movement of atmospheric motion and so on, and maybe there is a certain number of observations of temperatures and pressures and so on, and you as the neural network can do the rest. And for that reason, the possible advantage of neural networks in this setting is that they are not limited by using approaches that we already know and that we can already construct, and that they might come up with some better, unusual approaches for these kind of problems that might be more efficient, might be, let's say, less computationally intensive, might be quicker or more reliable in the long run. That's the sort of the flexibility, I think, is one thing that's really nice about that. And that ties in with another sort of thing that limits classical methods. So once you've decided, let's say, a differential equation or something like that, that's pretty much as you can, as accurately as you can model the physical system. Once you have your differential equation, that's kind of the accuracy you get. But in many cases, the sort of physical systems are actually dependent on so many different factors that it's not easy to bring that into a simplified model. And with machine learning methods, it's generally speaking a little bit easier to bring in data and to sort of account for things that we cannot understand in detail directly.
So you might have, in a classical method, you might have differential equations that bring into play factors to do with the fluid dynamics of the atmosphere or something like that. But then you're kind of limited. That's the information you can input into the system. But if you use if you use a PIN, you have that information, but you can also bring in other data that's available and see if it can learn something from there.
Exactly, yeah. So maybe there is some variables that are relevant to the behavior of the weather, like physical parameters that we just don't know or that we cannot incorporate. I think current weather models use a few dozen relevant parameters, including pressure and temperature, but there might be some others that could play into it and that we cannot capture on the model basis, I think. Yeah.
You said that at the moment it's, some successes in the research area, but can't be scaled up. So what are the challenges at the moment with pins in scaling them up or using them more widely?
I think there's sort of two very big ones, and it's also the ones that we kind of identified in that working group and that we're really trying to sort of tackle a little bit. And the first one is sort of a certain sense of a guarantee of getting the right solution. And this is something that's challenging with machine learning methods, broadly speaking, and especially neural networks, that there aren't too many sort of theoretical guarantees that tell us that the methodology will always give us the correct answer. And so one example where that comes up, although sort of architecture-wise and mathematically the systems are quite different, but you might have heard of sort of hallucinations in large language models. And this kind of issue, there's nothing theoretically on a theoretical basis that prevents this from happening when you use a machine learning method to make predictions about nature.
So when you talk about hallucinations, could you tell me what you mean by those in terms of the large language models, and then how that might look and impact the situation with pins?
Yeah, very sort of broad comparison. In a large language model, you might ask it to provide you with some references for your research. And I think that could be scientific research, but in the news we've seen more often legal research, so for case law and so on. And the language model might provide you with some titles and citations of specific examples that would be relevant to your work, but actually those don't exist, right? And they look just as real as if you had found the actual thing, but if you don't go and verify, then you can't be sure that really is there. So it's kind of making up some data, and the same sort of phenomenon can occur when you use machine learning methods to simulate physical systems. So if you, for example, want to simulate the flow of a fluid, then a machine learning method might give you something that to the eye looks correct, but actually, for example, it might have the wrong pressure in certain areas. And that could mean that, for example, it's missing a significant weather system over part of the UK or somewhere else. And this kind of sort of outputs that seem possibly accurate but are not guaranteed to be are really tricky because you would need something else to verify that. Yeah.
That's really interesting, because I'd heard about the hallucinations like from ChatGPT and things,
exactly.
But I hadn't thought about how that could come up in other kinds of machine learning. So that's really interesting.
And Georg told Rachel about the second challenge researchers from Maths4DL are working on, and that's to do with the fact that machine learning algorithms can get horribly stuck. That's because when they're in the learning or training phase, what they're trying to do is minimize a loss function, which basically measures the error in their outputs, and it's this error that they want to minimize. You can think of this minimization as finding the lowest point at the bottom of a deep valley in a hilly landscape. As Georg explains, when the algorithm hits a local low point and gets stuck there, then nothing, not even more computing power, will help it get out, even though there might be even lower low points further afield. Now, this is a big difference to classical methods, which don't get stuck in this way. In classical methods, you can always improve your answer if you throw more computing power at the problem. Here's Georg again to explain.
And then the second approach is something that's maybe a little bit more specific, but somehow also counterintuitive. So for these classical methods that people use for weather forecasting or again for structural simulations and so on, there's this paradigm that you can give the methodology more computational resources, And if you increase the computational resources, let's say you let it run for a few days extra, or you have a few more computers to run on, then you typically get a better answer, a more accurate answer, which is really nice. And that sort of thing works until to a very, very small number, which is an inherent limitation of computers. It's called the machine accuracy. But up until that number, which is so small that it often doesn't really influence the kind of behavior you want to simulate, you can definitely get better answers with more resources. But with machine learning methods, it's actually a little bit different. And so while it's still true in the very sort of early settings, if you let your computer run for a second, you're certainly not going to get a good answer. But if you let it run for a few hours, then maybe you might. There is a barrier that currently people cannot break. And so it seems that after you've sort of reached a certain point, giving the computer more resources, at least the way we currently think of giving more resources, isn't really helping the model.
That was the other thing that had come up in various discussions I'd had, which is this idea that usually you can let your computer run longer, make your iteration step smaller in some way, and you should improve the outcome. And that's a standard approach in classical methods, exactly. But it doesn't seem to work reliably for machine learning. Is that right?
Yeah, that's correct. And in essence, it has to do with something I said earlier, which is that machine learning methods can sort of, they don't rely on our previous knowledge of how we construct or how we approach problems, right? And I think a lot of work has really gone into designing numerical methods that are what's called stable. And that's exactly this kind of feature that you can sort of increase power or decrease time steps and so on and get better and better results. But machine learning problems, the way they work is that there is this sort of training aspect to all of this. And in the training phase, essentially what the machine learning method is trying to do is trying to minimize a certain cost. And that cost doesn't have the same sort of simplified mathematical properties that we like from classical methods. And as a result, it's what's called a highly nonlinear optimization problem. And you might find that you don't actually find the best solution, but you find a solution that looks like it might be a good solution. That's called a local minimum. And it's there where the sort of things go wrong and where it's problematic.
And so if you hit that local minima, it doesn't matter how much more power you put in, you're kind of stuck in that local minima and you can't get to the better solution.
Yeah, at least with the kind of training or optimization algorithms that we currently have, because these kind of training algorithms are usually based on gradients, and that means they see only very local information about the loss function, the optimization that you want to perform. So that means if you're in a local trough, you just see if you look left, it's going up. If you look right, it's going up. But it doesn't tell you that maybe beyond that hill, there's actually a deeper hole that you might like to go into. And yeah, so with current methodologies, it's a big problem.
You organized one of the workshops within the Maths for DL research program. What were you hoping would happen at that workshop, and what did you find most interesting and exciting about what you did over those 2 days?
So yeah, so I had just started organizing this, so it's in the very early stages for me. But I think my goal in this first event was really to try and bring in people from as many different backgrounds as possible, because like there are really, really tough challenges with machine learning methods. And I think the more different points of view and different kind of experiences we can get in, the more likely it is that we'll find a good resolution to these kind of challenges. And I think from that point of view, it was actually really positive, because on a personal level, I had really interesting discussions throughout the day, and saw a lot of different points of view to approach these kind of problems that I may not have thought of before. And I think as a working group together, we probably now were able to distill this sort of most promising of those ideas that we can then focus on and sort of continue working on as a group. So I think that was really great. And also I think just seeing the variety of settings in which machine learning is used and especially pins are being used is pretty cool. And the fact that we had some people from industry there as well was really exciting. I think that there is interest in using them in practical settings.
It's quite interesting to talk to you at this point when it's such new methodology. Like, is that how it normally works when people are developing new methodologies? This kind of really, it feels quite collaborative. It feels quite, bringing together a lot of people. Is this how this normally progresses? Like new methodologies are developed, or is this a slightly different way of doing it?
Yeah, no, definitely. I think so. I mean, I've never been involved with a real sort of huge change of approach or something like that, and there have been a lot of over the recent decades. But in principle, I think it is really that a lot of really good ideas just come about by coincidence, and if you bring the right people together, then there's more chance to get those right ideas in the same place.
That was Georg Maierhofer from Maths for DL talking about the importance of getting the right people together at the right time when trying to solve problems in mathematics and in machine learning.
Georg was talking about his work on physics-informed neural networks, or PINs, with the Maths for DL research group. You can find out more about machine learning and some of the work that Maths for DL are doing by going to plus.maths.org/maths4dl. That's maths, then the number 4, then DL. We've also included a link in the show notes. That's it for this episode of the Maths on the Move podcast. Thanks for listening and bye for now.